Welcome to this explainer. If you've ever felt completely overwhelmed trying to model the wild, constantly shifting behavior of software, well, you're in exactly the right place. Today, we're going to demystify UML state chart diagrams and learn how to take all that chaotic behavior and map it into perfect visual order.
So, let's jump right in. Think about a really fundamental problem in software design. How do we actually organize the totally unpredictable actions of complex systems? I mean, software isn't just static data, right? It's alive. It reacts to user clicks, it waits for timers, it throws errors, and it's constantly changing its state based on all these events. Trying to keep all of that in your head, or worse, buried in thousands of lines of spaghetti code, is just a recipe for disaster. We really need a visual blueprint.
Here is our roadmap for today. We have 5 sections. First, an intro to state machines, followed by the anatomy of a state, the rules of transition, tackling composite states, and finally, pseudostates and submachines.
Section 1, Intro to State Machines. Let's start with something as basic as a simple desk lamp. At any given second, that light bulb is in one of 2 distinct conditions, or states. It's either off or it's on. You start at the beginning, an event like turn on moves you to the on state, and turn off brings you right back. And hey, if the bulb burns out, you just follow an arrow to the final state, which terminates the sequence entirely. This simple, elegant loop is the beating heart of all state chart diagrams. Moving on to Section 2, Anatomy of a State.
Now, a state isn't just some passive waiting room. Stuff actually happens in there. Inside a state, UML gives us 3 specific labels for internal activities. First is the entry action, which triggers the exact millisecond you enter the state. Second is do, which is an ongoing activity that just keeps running as long as the state is active. And third is exit, the very last thing that triggers right before you transition out.
Let's apply this to a real-world object, say a coffee grinder. Imagine you're in the grinding coffee state. The absolute first thing you do, your entry action, is close the dispenser door, because obviously you don't want coffee grounds flying everywhere. The do activity is the actual physical grinding of the beans. And your exit action? Opening the dispenser door to release the grounds just before you leave the state. It's incredibly logical. But what if something happens while you're in a state and you don't actually want to leave it? Well, that's called an internal transition. For example, if a user hits a key and a quick true or false check confirms the grinder is currently running, the machine might just emit a beep. You evaluated an event and triggered an action, but the machine is still actively grinding coffee. You never left the state. All right, Section 3, the rules of transition. So, how do we actually move from state A to state B? It comes down to a really strict syntax made up of 3 things. First, the trigger, the event that kicks things off, like pressing a button. Second is the guard condition. This is your Boolean test. It has to evaluate to true for the transition to fire. If it's false, nothing happens. And third is the effect, the actual activity that runs while the transition is happening. When you visualize this on a transition line, it suddenly makes perfect sense. You've got your triggers up front. Then, tucked right there in square brackets is your Boolean guard condition. And finally, after the /, you have your effect. This one single line of text tells a comprehensive, precise story about exactly how a system changes. And hey, transitions aren't just about active user clicks. Time is a huge factor here. UML gives us 2 really handy keywords for this. After is used for elapsed time, like automatically freezing an overdrawn bank account after exactly 3 months. When, on the other hand, is for absolute time, like firing an event when the date hits exactly March 20th. This brings us to Section 4, Tackling Composite States. As systems scale, they get messy fast. To organize things, UML gives us 2 types of composite states. Think of them as big, overarching states that contain smaller substates inside. The first is a simple composite state, or state, meaning the system can only be in one of its substates at a time. The second is an orthogonal composite state, or AND state. This one is an absolute game changer because it handles concurrency. Take a look at an OR state for a vending machine. We have this big dispensing state, and inside, it's a strict step-by-step sequence. You rotate the rack, you release the drink, you open the door, one thing happens at a time. To the outside world, the machine is just dispensing, but internally, it's following a very specific single-file path. But check out the AND state. We split that dispensing state right down the middle with a dashed line. That line literally represents parallel processing. On one side, we have that exact same physical dispensing sequence. But simultaneously, on the other side, the machine is handling its bookkeeping, logging the purchase, and updating the digital inventory. Two independent things running at the precise same time, contained in one simple box. Let's put this into practice with a microwave oven example from our source material. The prompt states, for safety reasons, the oven should not operate when the door is open, and on completion of cooking, a buzzer is sounded. So think about that. How do we map out power levels, timers, and those critical safety guardrails without turning it into a tangled mess? Well, here is the solution. It's like a giant puzzle coming perfectly together. You start at idle, move to setting the power, and then set the time. But look at the door guard conditions. If you open the door, it actively shifts to operation disabled. You literally cannot start the microwave until that door is closed, and the state moves back to operation enabled. It turns a bunch of chaotic rules into a foolproof visual flowchart. Finally, Section 5, Pseudostates and Submachines. To handle really massive diagrams, UML gives us pseudostates. I like to think of these as the traffic cops of your diagram. They don't actually do anything themselves, they just route the flow. You've got forks for splitting execution, history states that remember exactly where you left off if a process gets interrupted, and crucially, entry and exit points.
Let's look at a telephone system to see how this creates amazing modularity. If you have an on-hook state with transition arrows flying out randomly, it's just spaghetti. But if we turn on-hook into its own standalone submachine, we can route all those exits through standardized exit pseudostates. Now the phone neatly exits the entire submachine through a named portal. And we do the exact same thing on the receiving end for the off-hook routine. Everything, dialing, ringing, getting a busy tone, is hidden behind a neat little entry pseudostate. Any incoming transition just hits that entry portal and is smoothly routed inside. The result? This beautifully clean, high-level diagram. We've got two modular submachines communicating asynchronously back and forth. All that complex underlying logic is totally encapsulated. And the best part? If you ever need an off-hook routine in another project, you can just copy and paste that entire module. So we've covered a ton today, from simple on and off switches to the intricacies of concurrent submachines. You now have the exact building blocks needed to turn any chaotic system into a perfectly understandable blueprint. The only question left is, how are you going to apply these state chart diagrams to bring dynamic order to your next big project? Thanks for hanging out with me for this explainer.